In this video, I'm going to relate my latest design for an impulse drive and go over some interesting, but I would say inconclusive experimental results. But first, we'll review the basic idea behind an impulse drive. If you have a sinusoidal acceleration acting on a system and you do the cumulative integral of this acceleration to find the system's velocity, and then the cumulative integral of that velocity to find the system's displacement, you will find that the system does in fact displace. This is in spite of the fact that there is no net acceleration acting on the system. Because there is no net or average acceleration acting on the system could also be closed. A simple way to physically create such a system is to simply have two unbalanced masses revolve in synchronized circles in opposite directions. Because there is no net or average acceleration acting on the system, it cannot overcome external forces. The goal of impulse drive is to alter the sinusoidal acceleration such that it becomes asymmetric. If the peaks or valleys are wider and have different amplitude, the acceleration could take on an average value over its period. There's a simple way to do this in theory that is not so easy to physically create, and that is to simply alter the speed of a mass revolving in a circle in a very precise way. Here we have the path of a mass revolving around a circle, and we assume a specific distribution for the mass's speed over the positional angle theta. Here we can see that the red region is much faster than the blue. From the assumed position and speed of the mass, we can compute the derivative of its velocity to find the force that must be acting on the mass. From Newton's third law, it follows that whatever is constraining the mass to move along this path with this velocity will experience an equal and opposite proportional force. However, to discover the system's position throughout time, we must first reparametrize the system in terms of time. We do this by integrating the inverse of the mass's assumed speed over the arc length of the circular path. Because of the way we have started with an assumed speed and position as a function of the positional angle theta, time is not an independent variable, and we'll notice that if we plot time versus theta, it's not a linear graph. Now that we have values of time associated with each value for theta, we can integrate the reaction force created by constraining the mass's path with respect to time to discover if the reaction force has an average value, and we can see that it does. In theory, this system should be able to accelerate itself over time and overcome external forces. I have a few interesting videos of experiments with a real device designed in this fashion, but I would say they don't answer whether or not the device actually works in practice according to the theory. Basically because the effect is too small to be obvious and the influence of competing forces acting on the system is too large. This device is just an unbalanced lever arm turned by an electric motor. There's a magnet in the end of the lever arm and a band of magnets along the half arc of a circle. The magnets in the arc and on the lever arm have been arranged such that they repel each other, making it so that the speed of the lever arm slows down while traversing in front of the arc. The table that the device is on is sloped such that the left side of the frame is higher than the right. As seen in this video, the device moves up a slope, but there are a few problems with this test. The first is that the tension of the umbilical wires powering the motor definitely influence how the cart moves. The second is that the slope isn't steep enough that the cart rolls down it while the motor is off. So in this case, the device is technically overcoming gravity, but it has help in doing so that I've yet to completely eliminate.